Hi everyone, so today we're going to be talking about LINQ performance tips. This is video 2 out of who knows how many videos. And today we're going to be talking about type information and why losing type information is bad for performance. We're going to be looking at how LINQ handles structs versus classes. And finally, we're going to be correcting some stuff from my previous videos because some of you left comments that not all the things are accurate and some of the information is now wrong. So I'm going to be correcting that information as well. And let's move to the corrections first, I guess, because why not? Okay, so in the previous video, I've talked about the last operator from LINQ. And what I told you is that LINQ just uses the enumerable, so it will enumerate until it gets the last element and then it will return. And I've implemented the last operator myself using the indexer, and I told you that, that's why it's faster. But that information was true, but LINQ changed the implementation, and now the current implementation actually does check if we're having a list. So let's see the source code for that. Let's do the last. So we have the last here, and what it will do is it will do a null check. It will check if it's castable to IOList. If it is, then we're gonna do some additional checks, but we're gonna return the last element using the indexer, which is good, which is fine, which is fast. But in our tests that we did last time, we were still faster. So let's run the LINQ last version, which takes roughly what, 15 milliseconds, 14 milliseconds, something like that, right? Okay. And this is our version of the last. So our version of the last will just take the list and it will just return the last element. But unsurprisingly or surprisingly, depends on how we're gonna treat it, this version is way, way, way faster. And why is that? Because LINQ actually does the same bit. Is it the checks? Well, yeah, the checks are expensive. They're especially expensive in terms of branch prediction. So if we have a bunch of if statements and the processor will make a decision to go ahead and take the branch and it will be wrong, it has to like throw that pipeline away and get the new one, and it's going to be slow. But most of the time in this code it will not happen because we will always take the correct branch because we will always have this operation here in the loop, right? So there's no risk of taking the incorrect branch most of the time here. So what happens? So it turns out that interfaces are expensive. And what I mean by that, so if we have a enumerable here, then the problem becomes that this is an interface and we have to have a VLOOKUP table. So there's a virtual lookup, virtual dispatch table basically. It used to be like that, but now there's a new mechanism actually which got implemented not so long ago called VSD, which is virtual stop dispatch. This is a new mechanism that is more robust. It has additional features, and it should be, for instance methods, it should be faster, just a bit. So roughly what it will do is it will create a stop, and each time we need to call an instance method, it will look up the code from its like lookup table. It will do a bunch of things. I don't want to talk about them in great detail yet, but it will then generate that code, and the next of the calls will be just a simple like cache lookup because those values will get cached, and it should be faster than the old implementation. Of course, if we have multiple implementations of the interface and we will have a cache miss because of that, then it will fall back to the slow path version. But in our case, we should always have the fast path, but still this is a cost that's associated with it, even if it's cached, and we have to take that cost when we're using just interfaces. But it's good. I'm just trying to tell you that this mechanism is pretty good, but there's still some costs. There's always costs. So that's why we're slower. So there's a bunch of extra checks, and we're just operating on plain interfaces, and that's why. So let's measure the VSD performance actually, because we can. So I have a class called VSD here, and let's change that implementation here to VSD. And what we'll do is we're just gonna have a class that implements an interface. That's an empty method, do. And for one example, we're just gonna call the interface, and for the second example, we're just gonna call the class. And let's check the performance. So 32 milliseconds, 25, it's gonna default to 25. Okay, so 25 milliseconds for the interface implementation. So now let's go to the concrete class. 3.5, 40 milliseconds, 3.1, yeah. So roughly speaking, this is the overhead that's associated with this. And like I said, there could be more costs because we're just using the single implementation of a single interface. It's going to be a bit worse where we have like class B, class C, class D, and they all implement the EI interface and they all have method do, but this method is completely different from each other. So that's going to be a bit slower in this situation, but we don't have this cost here. All right, so let's move now to LINQ performance. So let's look at preserving type information, because we just learned a bunch of stuff about interfaces and about concrete classes. And if you wanted to know more about VSD, there's this article here about VSD, so Virtual Stop Dispatch. So if you just type into Google Virtual Stop Dispatch or VSD and add C#, you're gonna get this implementation. VSD is a technique not exclusive to CLR or dotnet. There's a couple of different implementations of this technique in a couple of different languages, runtimes, and what have you, but this is specific to .NET. So if you want to know how this works in .NET, go here. And by the way, vtable is still here because VSD cannot handle currently virtual stubs, but maybe someday. Okay, so moving on. Moving on to the problem why interfaces are bad as well. So what we have here is find first method. We have the same list here. We're still gonna do first or default. We're gonna check if the item is greater than this guy here. So we're gonna put a 9, and hopefully we're gonna return this element. So all good, right? Okay, so now let's check how it performs. And in my previous video, I told you that this is generally a bad idea because we were actually discussing a different method, but this method uses a enumerator. So that enumerator of our list will get boxed. So what do I mean by that? Let me give you just a tiny more context here. So this uses I enumerable, and let's look how the first or default is implemented. So this is first or default, but we're actually interested in this method here. So again, a bunch of null checks. We're doing the for each here, and we're checking against our predicate, and if our predicate is true, we're going to return the element. Otherwise, we're going to return the default. So what's the problem here? The problem is that a list has a enumerator, which is a struct. It implements all of the interfaces, I disposable, I enumerator, and I enumerator of t. And unfortunately for us, this will get boxed. We don't want it to get boxed, but it will get boxed anyway. And in order to be able to, show you that, let's comment this out for performance because we don't want to waste time on this, and let's fire up our debugger and let's see if we have a list enumerator that's on the heap. In order to do that, we're gonna dump heap, and we should see a generic list enumerator. So there's an enumerator here, but let's verify that it's actually ours. So our list is a very simple one which has elements from 1 to 10. So what I'm doing right now, I'm following the pointer to that implementation. So I have the implementation here. So this is my enumerator, and it has a field called list. And right now we're seeing our list, and our list has a array under the hood. So that's our array. Let's print it out. Let's see the elements. Remember, we have elements from 1 to 10. Very simple list. 1, 2, 3, and let's maybe look at the 10th element, 10. So it's our list. So that's what I'm trying to say. So it's our list. There's no mistake here probably. And we have unfortunately put an enumerator on the heap, and this is not what we want because we want to remain on the stack, because stack is faster, has better data locality, it's more predictable, there's no garbage collection here, so our pointers will not get moved ever, and it's better for cache locality as well. So we want to, preferably we would like to have our whole implementation on the stack, not on the heap. So how do we solve this problem for LINQ? Well, what we have to do is we have to retain the correct type information. So what I did here is I re-implemented the first or default, and I could just re-implement this signature here, but I just wanted to show you a different version. So I have a custom suffix in my function, otherwise it's exactly the same. And the implementation here is exactly the same as well as the linked version. So what we're gonna do extra here is we're gonna check if the source is a list. And notice that we're not checking against iList. And the reason for that is because we would have the same problem as before. We have to have a correct type information and concrete type information. So we're gonna do that. We're gonna cast a concrete type, and then we're just gonna have the same code as we had before, and that's pretty much it. And now let's fire up version 2. So 11 milliseconds, even 9 I'd say, yeah, 9 milliseconds, as compared to 2019, yeah, so it's around 19 milliseconds. 2 times faster, right? Is it 2 times? Let me check. 14, 9. Yeah, it's around 2 times faster, I'd say. Okay, so it worked. Now, let's verify if our enumerator is on the heap, or perhaps it's nowhere to be found on the heap, which is what we want, by the way. So let's go here, let's break, let's dump the heap, and yeah, not interfaces, no enumerators here. So that's good. That's pretty good. So why this version is around 2 times faster? So the first of all, we're not doing any allocations on the heap. We're just operating on the stack. That's good. The second bit is that we don't have any, interfaces, so we're not going to go through VSD. This is obviously faster as well, and all of these things combined give us the better performance. So it's all good, right? Well, no. So we have to be very careful when doing these checks, because if we have a system and we have a bunch of checks like that in every overridden LINQ method, it's going to bog down performance significantly because these are expensive. And I've talked about this a bit before about branch prediction. So the more stuff you put in here, the more likely that branch prediction will not hit the correct branch. And this will cause a significant performance downgrades. So you have to be pretty conservative with this, and you have to add this if you know that your dominant type into your system is, for example, a list or maybe a dictionary. Then you can add these two ifs and have good confidence that you're going to hit these branches, like all of the time. If you don't have that confidence, then you're just going to slow things down. So you have to be careful and you have to have data on hand. And in fact, now that I think of it, the LINQ version that I was referring to when having the last operator could end up the same way because they didn't have that check. They only added that check later because probably they had data on hand that everyone is using the I list. So or something that is a list and something that has the indexer. So it was like worthwhile to add this check here. Although we're not always going to hit that branch, and if we don't hit that branch, then maybe that's a problem. But it's like highly likely that we're going to hit that branch. So that's why they did it. Okay, so moving on. This is, like I said, you have to be conservative with these checks and you have to measure the performance of the system, and yeah, you have to be basing these checks on statistics. All right, so let's move to structs. So let me comment this out. Not yet. This is not a good time. So I have a struct called point here, and it has a bunch of fields. It has a string, which is a pointer in a struct, and this is interesting, to me. If you know what happens if we have a pointer in a struct, for example, what happens to the struct. But anyways, let's see what's gonna happen. So I have a bunch of points. They have a bunch of coordinates, and the example is the same as before. We're doing first or default, where x is greater than 1, which will return the last element of our array. And I have 3 versions of this code here. So we're gonna do first or default. The second version will do a for each, and the third version will just do the for loop and use the indexer to access the item and check. Okay, so let's run it. 70 milliseconds. 70 milliseconds. The second version will take 33 milliseconds, 27 milliseconds, something like that. And the third version will take 5 milliseconds. Yeah, it's around 5 milliseconds. Okay, so as you can see, there's a big performance improvement between this and this. And this version versus this version has significant performance improvements from like 02 to 03, right? And why is that happening? So that's not good. And let's check if we had a class, for example. What's going to happen if we're going to have a class here? Let's see here. It's 39, so it's a bit faster. And this version is 10. And this version is 2.5. So that's pretty good. What happens if we remove this guy, though? So for the class, that shouldn't make any difference. It's 10. It's 39. Yeah, so no difference here. What about the struct? 40 milliseconds. And now we have 19 milliseconds. So it got faster, it got a bit faster, and now we have 4.2, which is more or less the same, right? So what we did here is we deleted a pointer in a struct. And if we have a list like this, and we have a point, so it's gonna be still on the heap. nothing really changes because we have an array of points under the hood. So we're gonna land on the heap. What's going to be a bit different is that, when we're doing our for each operation, which is this case and this case, what we're doing is we're calling that enumerator, and that enumerator, what we'll do is it will do a defensive copy because we're we're operating on structs. So that defensive copy is something that we would not want to have, and preferably we would want, we would like that to be faster because we're doing a bunch of stuff that you don't want to do. So how to solve this problem? Well, we can use a data structure called refList, and that data structure behaves like a list with one difference, and that one difference is that it has a ref enumerator, and that enumerator is again your plain enumerator. Instead, it uses the current version, which has a ref return. So now what we're doing is we're doing ref returns. So that means we're not going to be probably doing a defensive copy of that struct. We're just going to return it by reference. So okay, let's let's test the performance now with this version. Let's start with LINQ because we're interested in like this sort of abstraction. So it takes now 14 milliseconds, so it's around 2 to 3 times faster already. Yep. So the performance is pretty good for LINQ. The performance for each should be pretty good as well. It actually shouldn't be indistinguishable from version with the for loop, and as you can probably tell, it's indistinguishable in performance right now. So our ref return enumerator is actually a benefit for us because all of these three versions are actually at a level of performance which I would call acceptable in high performance scenarios. So even the LINQ version is pretty good. And there's one catch here because, as you can tell probably, this does not implement IEnumerator of t, and it does not implement IEnumerable of t, which LINQ requires. So what I had to do here is I had to implement my own first or default, which operates on a concrete type of refList, and that concrete type is used to just do a for each, which is the same, almost the exact same thing as here. So what we're gonna do is we're gonna do for each, check the predicate. If the predicate is true, then we're gonna return it. Otherwise, we're gonna return the default version. So that's it, yeah. And this is an example where you can sort of tweak LINQ in these sorts of ways. I would not recommend doing it for like all of the things. There are frameworks like that actually. One of them is, I believe, called Hyperlink, which uses all of these things that I just mentioned. Not those things, but it does other things to make LINQ faster. So it will re-implement operations of LINQ to make LINQ faster. It will add new operators in to be able to express LINQ in more high performance ways as well. So I've been putting the hyperlink framework in my video description, so you should definitely check that out. Okay, so that's all for now. If you have any questions, if you think that I made a mistake, post that in the comments. I'm gonna try to correct each and every mistake if it's a mistake. And if you like the video, leave a thumbs up, subscribe, hopefully, and see you guys and gals, and really everyone next time in the next LINQ video. So yeah, thanks and bye.